Previously on The Mystery of Matter.
He realizes it's something fundamentally different has happened. This air is some kind of super air.
How could I explain this?
This subject is destined to bring about a revolution in physics and chemistry.
The discovery of oxygen really served as a starting gun for a worldwide race for new elements.
Davy had found a powerful new tool for the discovery of elements, the battery.
Nothing promotes the advancement of knowledge so much as a new instrument.
Eh bien, chers amis.
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following.
One of the oldest tricks in the chemist's toolbox is called the flame test. More than 1,000 years ago, Arab alchemists discovered that every substance gave off a telltale color as it burned. But as the number of elements grew, this test became less and less useful, because some elements gave off such similar colors it was hard to tell them apart. One day in 1859, a German chemist named Robert Bunsen described this problem to his good friend, physicist Gustav Kirchhoff. A few days later, Kirchhoff came to Bunsen's laboratory with an instrument made from 2 telescopes, a wooden box, and a prism. They used Bunsen's latest invention, the Bunsen burner, to heat their samples. Light from the burning element passed down the barrel of this telescope to the prism, which split the light into a spectrum of colors. What they saw when they looked into the eyepiece was a revelation.
You see a whole collection of sharp, bright lines at very particular wavelengths. And that map of lines is distinctive for every element.
It's almost like each element has its own barcode. It's a unique way of saying this is that element, not some other.
Like Humphrey Davy's battery, the spectroscope kicked off a whole new round in the discovery of elements, starting with cesium and rubidium, discovered by Bunsen and Kirchhoff themselves, quickly followed by thallium and indium, discovered by other chemists who seized on their new tool. Astronomers, too, embraced the new technology, turning the spectroscope to the heavens.
In fact, there's one element that we found by first looking at the sun. We didn't even know it was here on Earth. It was helium.
By the middle of the 19th century, there had been an explosion in the numbers of new elements that had been found. And this was exciting, but it also led to a kind of muddle. It seemed to have no order, no reason behind it.
Chemistry looked like an unruly garden, a jungle of bewildering details.
Human beings like to make things simple, and part of the whole scientific enterprise is to bring order out of what appears to be chaos, to bring simplicity out of complexity.
But the ever-rising number of elements, now up to 63, promised chemists just the opposite of simplicity, more and more variety, with no end in sight.
How many elements were there? Was this going to continue forever?
The man who would finally bring order to the elements was a young Russian chemistry professor named Dmitry Mendeleev. He didn't set out to be a savior. He was simply trying to organize the textbook he was writing. But as he grappled with this challenge over one weekend in 1869, Mendeleev would make a discovery for the ages. the periodic table of the elements. Today, it hangs in every chemistry classroom in the world, one of the most familiar images in all of science. But behind the table is a fascinating, untold story. Who was this man and how did he do it? Mendeleev had recently been named a professor at the University of St. Petersburg, the leading institution in Russia's capital. But getting there had been a long, improbable journey from humble beginnings.
Mendeleev was born in Tobolsk, Siberia, which is basically smack in the middle of Russia if you look at it on a map. It's very much the boonies of Imperial Russia.
His father, the headmaster of the local high school, went blind during the year of Dmitri's birth, leaving Mendeleev's mother to support and raise about a dozen children. Maria Mendeleeva sensed something special in her youngest child. So in 1849, she set out with her 15-year-old son on a 1,500-mile trip by horse-drawn sleigh in search of a school that would accept him. Like most students from the provinces, Dmitri was turned away in Moscow. But in St. Petersburg, he landed a spot in the teacher training school his father had attended. Exhausted by the journey, Maria died a few months later.
She took me out of Siberia and sacrificed what remained of her money, her life, so that I could get an education. From her, I learned that it is through work, not words, that we must seek divine and scientific truth.
Scientific truth was elusive for any young chemistry student in the mid-1800s. There were deep divisions in the field over even the most basic concepts, particularly the atomic weights of the elements. Most chemists believed each element had its own unique kind of atom, and ever since the early 1800s, they'd been working to determine how much an atom of each element weighed.
That's how one distinguished one element from another. So it was crucial to understand what were the correct atomic weights for each of the elements.
Everyone agreed that hydrogen, the lightest element, should be assigned a weight of 1, and that heavier elements should have proportionally higher weights. But that's where the agreement ended.
Did carbon weigh 6 or did it weigh 12? Did it weigh 4? That depended on who you talked to and when you talked to them. By the late 1850s, people were incredibly confused.
This was an unsupportable situation. Something had to be done.
Hoping to sort out the mess, chemists organized their first ever international meeting, held in Karlsruhe, Germany in 1860.
Mendeleev, being a young enterprising student, goes to this meeting and he hears a very important speech by an Italian chemist, Stanislao Cannizzaro.
Cannizzaro laid out a persuasive case for a new uniform system of atomic weights.
I still remember the powerful impression Cannizzaro made. He seemed to advocate truth itself.
After Karlsruhe, something astonishing starts to happen. Within a few years of the Congress, you start seeing lots of different attempts to organize the elements that are all based on these new post-Karlsruhe weights.
A French geologist arranged the known elements in a spiral along the outside of a cylinder, like the stripes on a barber pole, and found that elements with similar properties tended to fall into columns. An English chemist arranged the elements by atomic weight in rows of 7, and found that their properties repeated like musical notes 1 octave apart. By the end of the 1860s, 5 different European scientists had detected glimmers of a hidden order among the elements, but no one could quite put the puzzle together. That's where things stood when Mendeleev finally landed a professorship at the University of St. Petersburg. One of the duties of his new post was to teach introductory chemistry.
He has to teach this class, hundreds of students, and he has to give them a textbook. There are no up-to-date Russian language college-level textbooks available.
So Mendeleev set out to write his own, Principles of Chemistry, in 2 volumes. He completed the first volume in 1868, and on Friday, February 14, 1869, he sent the first 2 chapters of Volume 2 off to his publisher.
Marina,
He was in a hurry to finish it because he was struggling to make ends meet.
То же самое место, номер 36.
He hasn't yet gotten any royalties from the textbook because it hasn't been written yet. He's got to keep his family fed and clothed. He has, at this point, 2 children and a wife, so he was always looking for more funds.
To make a little extra money, Mendeleev planned to take a short break on Monday to do some consulting for a cheesemakers cooperative. But he had something on his mind. His publisher was expecting the next chapter of his textbook in 2 weeks, and he still hadn't settled on a way to organize the rest of his book. Mendeleev had spent most of the first volume covering a few common elements like hydrogen and oxygen in great detail.
You learn a huge amount of chemistry, but it's slow. Volume 1 contains just 8 elements out of the 63 that were then known.
When it came to writing the second volume of his textbook, Mendeleev realized that he had better find an organizing principle fairly quickly because he had to cover the remaining 55 elements.
Since I'd set out to write a book called Principles of Chemistry, I felt I had to establish a system for classifying the elements. A system based not on chance or guesswork, but on some sort of principle.
Изволите чай?
The problem gnawed at him all weekend.
He's trying to come up with a way of packing more elements in the same amount of space. He couldn't ramble the way he did in Volume 1, however useful that was.
Mendeleev had already hit on the idea of focusing on whole families of elements rather than treating one at a time. Chemists had long known that certain elements resemble each other in much the way family members do.
You can often tell people are related because they have the same sort of face.
They have the same nose, they have the same color eyes. There's something in common, and that's something very similar in these chemical families. They tend to react similarly to the same kinds of substances.
Mendeleev had ended Volume 1 with 2 chapters on a well-known family, the halogens: chlorine, fluorine, bromine, and iodine. He began Volume 2 in the same way, with chapters on sodium, potassium, and lithium, a family called the alkali metals.
He realized that a family of elements is a good way of organizing so you can do more with less space.
The problem was there was no obvious family to turn to next. For insight into what other elements might be grouped together, Mendeleev looked more closely at the 2 families he already had.
And in that process, he figures out something rather extraordinary about the elements. He looks at the atomic weights of sodium and lithium and looks at the difference between them. And then he does the same thing for fluorine to chlorine and notices that those 2 differences are very close to each other.
Was this just a coincidence or a clue? Excited, Mendeleev wrote down the lightest elements and their atomic weights. After 7 elements, he broke off and started a new row, keeping elements with similar chemical properties in the same column. The numerical pattern continued to hold.
The eye is immediately struck by a pattern, a regular change in the atomic weights of the elements within the horizontal rows and the vertical columns.
He notices that there's a regularity in the differences. That is, the changes that happen within a family happen regularly across families. And that's the fundamental insight that gets him thinking about how to organize all the other elements.
Mendeleev had begun the weekend trying to solve the problem of what to do next in his textbook. But having reached this aha moment, he dropped everything else and he poured all his energy into revealing an absolutely fundamental principle of nature.
When he was taken by an idea, he was really taken by it. He starts putting together this system, and he's trying to figure out the hard spots, the things that don't quite make sense. Maybe I can scratch out this element here and put this element in its place. Should I change the atomic weights? Do I have to rethink their properties? And the problems of it, the intellectual puzzle, just grabs him.
The challenge Mendeleev faced was similar to one of his favorite diversions, the card game called Patience, in which the object is to arrange playing cards by both suit and number.
That process of keeping several different variables in mind is kind of analogous to how Mendeleev was thinking. He started using both the regular increasing order of atomic weights and the relationships of chemical properties with each other to build two dimensions.
Mendeleev didn't just lay out the known elements in order of rising atomic weight.
When it looks like the next element doesn't have the properties it's supposed to have, he scooches it over and leaves a blank spot.
And has the audacity, has the daring to suggest that there might one day exist an element that would fill that space.
The few scraps of paper left from Mendeleev's struggle that weekend reveal that he sometimes arranged the chemical families in rows instead of columns. Unhappy with this early attempt at a table, he moved the alkali metals to a new position in the next draft below, but kept them together.
Mendeleev is not moving elements individually, but he's moving them as a block. It's as if it's a composite piece of a jigsaw puzzle that he's moving all together.
On Monday morning, a driver arrived to take Mendeleev to the train station for his trip to the cheese cooperative. He was well into his task, but still struggling to make all the pieces fit. We know this because one of the surviving fragments is a letter delivered that morning concerning arrangements for his trip to the cheese cooperative.
And on the back of the letter, which still bears the stain of a cup, Mendeleev has sketched a few symbols and has carried out some very simple calculations. He's looking at differences in atomic weights.
So he was still working on the problem, even after wrestling with it all weekend.
Карета ждет вас внизу.
The drafts of Mendeleev's table show plainly the struggle he went through.
At the bottom of the page, he lists the elements to be classified. As he fits them into the table on that page, he crosses out the elements. It's just what you and I would do. We can see the effort in that page. He's making mistakes, he's correcting them. It's full of crossings out. There are things that don't quite fit. This is a human being trying to understand this world.
Hour after hour, Mendeleev worked on the table, missing one train after another. Finally, he dismissed the coachman. The cheesemakers would have to wait.
Кто там?
Александр Алексеев приехал.
Дмитрий Иванович, здравствуйте.
That afternoon, a visitor found him distraught, unable to capture the order he knew was there, just out of reach.
Не могу найти. Ничего, у вас все получится.
Later that day, Mendeleev came to a choice that would crystallize his thinking. The elements involved were iodine and tellurium.
Iodine's a little lighter than tellurium, so it should come first. But Mendeleev looks at that and says, well, if I put iodine first, it's in the wrong family. It's actually a halogen, which is the next row down.
If he stuck to that weight rule, it would put an element outside of the family it obviously belonged in.
So he decides tellurium, the heavier element, should go first. It always bothered him that iodine was lighter than tellurium but came after. That breaks the order of atomic weights, but it preserves the family resemblances, which are more important than just the increase of atomic weights.
With that principle established, Mendeleev hurried toward the end.
And the more he worked on it, the better it looked.
Finally, that evening, Mendeleev completed his table. Before leaving the next day, he ordered 200 copies printed and sent to leading European chemists.
By the time he left for the cheese factory, Mendeleev knew that he was onto something extremely important. I think he realized that day that he had cracked it.
With a few modifications, soon made by Mendeleev himself, his 1869 draft is easily recognized as the periodic table of the elements, incomplete but unmistakable. In his published table, Mendeleev left blanks for some of the elements he thought were missing.
Not only did he leave a blank space, but he suggested an approximate atomic weight for that future element.
And the fact that Mendeleev on that first weekend is already thinking this way, that's a sign that he believed that there's something deeper going on here.
Mendeleev believed his table was more than a convenient way to arrange the elements. He was convinced he had discovered a law of nature, that the properties of the elements are determined by their atomic weights and vary in a regular, periodic way across the table.
It's periodic because the properties of the elements repeat in a regular fashion. When you wrap around from one row to the next and come back to where you were, the elements that are in the same column have similar properties.
He had an almost mystical feeling that this was there in nature and not so much a human invention as a discovery.
Given the remarkable regularity of his table, Mendeleev couldn't believe nature would have just left some spaces empty.
Laws of nature do not permit exceptions.
There must be an element which we have not yet discovered. Go look for that element.
And he was bold enough to not only to say an element is missing, but to predict.
The periodic law allows us not only to predict what new element will be found, but also to determine in advance their chemical and physical properties.
In 1871, Mendeleev published an article making predictions about 3 of the missing elements based on the properties of their neighbors in the table.
Chemists really weren't used to making predictions of any kind, let alone ones to this degree of specificity. They are remarkably precise and quite daring for Mendeleev to print them.
4 years later, a French chemist found a new metal so soft it melted in his hand. He called it gallium. It seemed to be a good fit for the empty spot below aluminum, but the density didn't match Mendeleev's prediction. He wrote the Frenchman suggesting that he check his data.
So you can just imagine this Frenchman who actually has the element in his hands, hearing from this Siberian who has never seen the element, and daring to say to him that he's made a mistake.
But sure enough, when the French scientist rechecked his measurements, Mendeleev was correct.
So not only had Mendeleev predicted the element, but he knew the properties of the element better than the discoverer of the element knew them.
Within 15 years, all 3 of the detailed predictions are discovered, and that catapults Mendeleev to chemical superstardom.
I never thought I would live to see my ideas verified. I was wrong.
But in 1894, 2 British scientists made a discovery that threatened to bring Mendeleev's carefully crafted edifice crashing down. They found a new gas they called argon that didn't seem to fit into the table.
When Lord Rayleigh and William Ramsay discovered argon, it looked like a problem, a very serious challenge to the periodic table itself.
Mendeleev's first reaction to almost anything that was contradictory to the system was to be hostile to it and suspicious. And Mendeleev therefore decides it's not an element. There are lots of reasons to think that. First, it doesn't react with anything.
Chemists couldn't get it to do anything. It was inert. It behaved like no other gas that anybody had ever encountered.
And secondly, it has no place on the table, so how can it exist?
Matters got worse when Ramsay announced he'd also isolated helium, 30 years after it was first detected in the sun. It was definitely an element, and it too had no place in the table.
And then just 3 years after that, William Ramsay's research group discovered 3 new rare gases, krypton, xenon, and neon.
They display the same kind of properties, they're all inert gases, and they display the same increase of atomic weights as the other natural families do.
And that changed the situation dramatically. What began as a single anomaly, a single puzzle, now looked like a group of elements.
Now we can see that helium, neon, argon, krypton, and xenon are as closely united as any other group.
And so Mendeleev makes the single biggest revision to the system he ever did. He puts in a new column, and that is the family of noble gases.
My periodic system is in no way injured by these discoveries. In fact, they confirm and strengthen it.
It turned out to be a vindication of the periodic system. and if anything, made it even more profound, the discovery.
Mendeleev's table had finally brought order to chemistry's unruly garden.
After Mendeleev, one could see that each element had a place. It was a grand design that worked.
Chemistry wasn't just one thing after another, random substances we've dug up from the earth. They are interlinked in a complicated and rich way.
We are at the dawn of a new era in chemical science, approaching a new understanding of the still mysterious nature of the elements.
As the 19th century drew to a close, the periodic table's ability to corral the elements contributed to a growing sense that the work of science was just about complete. Most of nature's building blocks had been found, measured, and cataloged. Chemists agreed these elements had been and always would be the same, forever fixed, unchanging. All that remained was to fill in the few remaining blanks. Or so it seemed. In fact, this smug sense of satisfaction was about to be shattered by something and someone completely unexpected. She was the unlikeliest of revolutionaries. A graduate student, a woman from Poland, who had left her homeland to pursue her passion for science in Paris. Yet in 4 short years, her discoveries would transform our understanding of matter and make her one of the most famous women in the world.
She worked on something that was relatively obscure and turned it into a blockbuster. New elements, new properties, and a whole new way to look at the world.
The world would know her as Marie Curie, but she was born Maria Skłodowska into a family of Polish patriots at a time when Warsaw was under Russian rule. Poland had been literally wiped off the map, its residents forbidden to speak their own language or teach their own history. But Maria's family secretly defied the Tsar, speaking Polish at home and reciting patriotic poetry to preserve their Polish heritage.
She used to go by an obelisk erected in honor of the Russian people and spit on the obelisk on the way to school. So you can see Maria learned early to be a fighter and resistor.
The daughter of 2 teachers, Maria excelled in science and math. But in Russian-ruled Poland, women were not allowed to attend university, let alone become scientists.
Very, very few places in Europe or elsewhere had opportunities for young women to study science. So one of the few places that she could was, in fact, in Paris.
But because her family was too poor to send her, Maria would first have to work for 6 long years as a governess to support her older sister's studies. Only at age 24 did she finally get her chance.
She waited her turn and she didn't give up. And when the turn came, she took it.
I was lost in the great city. But the feeling of living there alone and taking care of myself without any help didn't depress me at all. I had been waiting for this opportunity for a long time.
Paris in the 1890s was like no other place on earth, a living showcase for the wonders of science and technology. The city boasted such modern marvels as electric streetcars and telephone exchanges. At the laboratories of Louis Pasteur, scientists were conquering diseases that had plagued humanity for centuries. The Lumiere brothers were thrilling crowds with their new invention, pictures that actually moved. And rising above it all was the brand new Eiffel Tower, which would remain the world's tallest structure for nearly half a century.
Here was Paris, a kind of intellectual, artistic, technological capital of the universe. This is where the modern age was born.
She felt this precious sense of liberty. She could say whatever she wanted, go wherever she wanted. She took it all in and loved it.
Everything I saw and learned was a new delight to me. I had only one regret. The days were too short and went by too quickly.
Adopting the French form of her name, Marie, she enrolled at Paris's preeminent university, the Sorbonne, where she could study under the leading lights of French science. One of them was Gabriel Lippmann, a future Nobel Prize winner.
Another was Henri Poincaré, who was one of the leading mathematicians of the 19th century. One of her math instructors was a mountain climber, another was an aviator. These were exciting people, scientists who had exciting lives.
It was like a new world opened to me, the world of science, which I was at last permitted to know in all liberty.
Marie graduated first in her class in physics, and with Professor Lippmann's help, received a grant to do research on magnetism. A friend suggested she seek out a French physicist who had studied the subject and might have some lab space for her. The meeting would change her life.
Pierre Curie seemed to me very young, though he was 35 at the time.
I think it was pretty much electric from the beginning.
With all my heart, I thank you for your photograph. I showed it to my brother Jacques. Was I wrong? He finds you very fine, but he also said she has a very decisive look, maybe even stubborn.
Pierre Curie was a first-rate researcher, but he had never bothered to complete his dissertation and was content teaching at an industrial college.
He was diffident, modest, and shy. He was very much an outsider. He'd been homeschooled by his politically radical father, along with his brother Jacques.
In a family photograph, you see him with his brother. His head is resting on his hand. It's a pose of dreaming, as if he is looking at some inner vision.
Pierre was a man of ideas, not action. But he was galvanized by this young woman and pursued her as he had nothing else in his life.
It would be a beautiful thing if we could spend our lives near each other, true to our dreams, in science, where every discovery, no matter how small, lives on.
Pierre's proposal posed a dilemma for Marie. She had planned to get a first-rate scientific education in Paris and then return to her beloved Poland to teach and care for her aging father.
Her mother died of TB early on, and he was counting on Marie coming back.
Now this ardent young man was offering her an exciting life as a working scientist.
It was a decision that would mean abandoning my family and my country.
Marie had all those feelings of responsibility for her father, for her family, and then for Poland on top of that.
In the end, their mutual devotion to each other and to science overcame Marie's resistance.
She wrote one of her friends, "Fate has brought us together, and we simply can't bear to be apart."
The newlyweds left on a cycling honeymoon after a simple ceremony in 1895. By 1897, even with a toddler to care for, Marie had set her sights on getting what no other woman had ever received in France, a doctorate in physics. At the time, the world was abuzz with excitement over a new discovery: mysterious rays that had the power to see through solid objects.
You could, by this process, look at the bones inside of your living hand. It's as if you had a magical set of glasses that lets you see inside of living creatures, and that sparks the public imagination.
Doctors instantly recognized X-rays as an invaluable diagnostic tool.
There was a great rush of excitement from working scientists as well. In that first year, there were about 1,000 scientific articles published at a time when the entire physics community in the world was only about 1,000 members.
But with so many others doing research on X-rays, Marie felt it would be hard to make an original contribution.
And so she picked something that she could work on where there was less competition. In fact, no competition.
Just a year earlier, a French physicist named Henri Becquerel had discovered a different kind of ray given off by the element uranium. These uranic rays were powerful enough to penetrate thick black paper and create an image on a photographic plate. But the images were not nearly as striking as those created by X-rays, and they seemed to have no practical value. So after writing a few papers about this scientific curiosity, Becquerel dropped the subject, thinking it had been squeezed dry.
Marie just thought that this was a tremendous thing to work on, particularly as a graduate student.
The subject was attractive to me because it was entirely new. Little had been written about it.
There was another reason Becquerel's uranic rays appealed to Marie. She had spotted a clue that might reveal more about them. As you can see, air is normally a poor conductor of electricity. The current can't jump this gap, so the bulb doesn't light. But Becquerel had noticed his uranic rays had the mysterious power to charge the air around them, allowing electricity to leak across. The amount of electricity was incredibly small, about 1/trillionth the amount needed to light this little bulb. No meter of the day could measure it. But Marie had a secret weapon Becquerel didn't.
Right in Marie's own household was perhaps the world expert in how to measure tiny little electrical effects. The two of them, Pierre and Marie Curie, designed this really quite ingenious instrument to measure these very subtle electrical effects from her samples.
They placed a layer of uranium on a metal plate, then charged the plate with a battery. As expected, electricity leaked across the gap to the plate above. To measure this tiny current, the Curies would use this second device to create a matching amount of electricity. Inside was a special crystal that could generate its own tiny charge thanks to a phenomenon called piezoelectricity. More than 20 years earlier, Pierre and his brother Jacques had discovered that certain crystals give out electricity in response to pressure.
The amount of electricity generated when you squeeze or stretch that crystal depends precisely on how hard you press on that crystal. And that means you have a way to make a very, very sensitive measurement of minute little electrical currents.
By placing a weight on the pan below, Marie stretched the piezoelectric crystal inside the device. Then, by slowly relieving the tension, unstretching the crystal, she could generate a charge exactly offsetting the one coming from her uranium sample. She could tell the two charges were equal when the spot of light from this third instrument was at 0 on the scale.
Though it didn't look very pretty, this sort of pulled-together little contraption was exquisitely accurate and could allow them to make measurements like no one else in the world.
But using these instruments required extraordinary concentration and dexterity. Ever so gradually, Marie relieved the tension on the crystal, while carefully watching the spot of light to keep the two charges in balance, and timing how long it took to lift the weight entirely off the pan. The faster she had to remove the weight, the stronger the activity of her test sample.
And that's why when you see pictures of Marie Curie in this experiment, she's sitting there with a stopwatch.
C'est bien.
Oh, la petite étudiante. C'est très bien. C'est encore.
I never dreamt that I was about to embark on a new science that Pierre and I would follow for the rest of our days.
Day after day, working in a cramped, unheated storeroom, Marie painstakingly carried out her measurements. She compiled data on uranium, then went on to test the other known elements to see if any of them could also electrify the air.
She was not expecting to make any sort of earth-shattering discoveries.
She thought she would do some sort of diligent work on a whole lot of elements, and she would measure their power.
Exactly what you'd expect for a perfectly legitimate PhD dissertation.
And for a while, the results were predictably dull. No other elements showed this strange property.
Things were going along pretty routinely until one day in February of 1898, and that was the day that everything changed.
Pierre, viens voir.
In the course of a single week, Marie made two startling discoveries. She found that the element thorium could also make air a better conductor.
That was the first real solid indication that this was not unique to uranium. This might be a property of matter, not a curiosity of one particular element.
It was necessary to find a new term to define this new property of matter. I propose the word radioactivity.
The next surprise came when Marie tested pitchblende, the raw ore from which uranium is taken. Something was very wrong.
Comme ça, t'es sûr des résultats?
Je ne suis pas sûre.
Pitchblende seemed to be 4 times as radioactive as uranium itself.
When I find a result like that, as a scientist, my first reaction is, I made a mistake, or the machine isn't working.
She did what every good scientist should do, which was doubt it, be extremely skeptical, and check every last step of that chain.
So my mother made her measurements over again, 10 times, 20 times, until she was forced to accept the results.
In time, the Curies realized this was no mistake. The readings from pitchblende were real.
A light bulb went off and they said, well, maybe there's something else in there.
Very soon, they began to suspect that there was another element in pitchblende, which was producing this enormous radioactivity.
There must be some new thing under the sun, some new element that had never been seen before.
And it must be intensely radioactive since it was present in amounts so small that no one had ever detected it.
Since neither Marie nor Pierre was a member of the Academy of Sciences, they asked Marie's mentor, Gabriel Lippmann, to deliver the paper announcing this discovery.
This was one of the most important papers in the history of chemistry, and yet it was almost universally ignored.
Who was this Marie Curie? She was a graduate student. She spoke French with a Polish accent. She was married to a teacher in an industrial school, and she was a woman.
These are strikes that are definitely against you. And so her ideas just weren't embraced because she was so different.
But Marie knew she was onto something important.
She had lit upon, almost by accident, an extremely exciting discovery. And as soon as he figured that out, Pierre abandoned his work on crystals and joined her.
To track down their mystery element, Marie and Pierre subjected pitchblende to a battery of chemical procedures.
You break up your rock, you try to dissolve it, you treat it with all kinds of other chemicals.
The goal is to separate the ore into portions with different chemical properties, all the while tracking the radioactive signal.
She then throws away everything that isn't radioactive. It's getting more and more concentrated as she goes through these steps.
The Curies soon discovered that 2 distinct parts of the pitchblende, with different chemical properties, were both radioactive. That meant not 1 but 2 new elements might be hidden in the ore.
By July 1898, they were able to announce the discovery of one of those substances with certainty.
Marie, you will have to name it.
The former Mademoiselle Sklodowska thought of her occupied native country, whose very name had been erased from the map of the world.
Could we call it polonium?
Poland, remember, was still not a country. This was one way of putting it on the map.
Eh bien voilà, polonium it is.
Marie next turned her attention to the second mystery element.
She finds the activity is through the roof. It's nearly 1,000 times more active than even her uranium sample had been.
Marie's polonium sample had not been pure enough to yield a unique spectral line. Would this new, more powerful element pass the test?
By 1900, spectroscopy was often seen as the gold standard for identifying the materials you're working with. And if Marie Curie wanted to make some claim that she'd found, in fact, a whole new element, she was going to have to meet the chemists on their own terms. She'd need spectroscopic evidence.
Regardez ici. Il y a une ligne par ici.
Marie's sample showed the presence of the well-known element barium, but it also revealed a pattern of spectral lines never seen before. Strong evidence that she and Pierre had tracked down their mystery element.
She could tell that she had an element that hadn't been seen before, because the spectral lines she got were different.
And in the notebook, Pierre writes in very bold ink the name they decided to give the new element, radium.
But in the 19th century, there had been scores of claims of elements that later proved not to be elements at all. You needed to do more.
To satisfy the chemical community, a spectral line wasn't enough. They had to see the real stuff, which could be weighed, which could be measured.
It was important, as you would with any other element, to isolate this element, to weigh it, and to place it on the periodic table.
So in order to be absolutely certain, she had to have pure material, and that's what she set out to do.
It was my mother who had no fear of throwing herself into that daunting task. Without personnel, without money, without supplies.
To isolate even a speck of radium, Marie would need to process huge quantities of pitchblende, a job too big for her tiny laboratory. The only space available for this work was a drafty old shed, once used as a dissecting room for the school's medical students. As Greer Garson and Walter Pidgeon showed in the 1943 film Madame Curie, the Curies worked tirelessly to separate the radium from tons of pitchblende residue they had shipped from a mine in Bohemia.
Sometimes I had to spend the whole day mixing a boiling mass with a heavy iron rod nearly as big as I was. I would be broken with fatigue by the end of the day. And yet we spent the happiest days of our lives in this miserable old shed. An entirely new field was opening before us.
Marie soon realized that radium was a smaller part of the pitchblende than she ever imagined, less than 1/1,000,000th of 1%. Isolating it was going to be an enormous job.
Marie's daughter said that had it been up to Pierre, he might not have taken the next step.
The world has done without radium up to now. What does it matter if it isn't isolated for another 100 years?
I can't give it up.
There is a special passion which goes with the discovery of elements, and a line in the spectrum is not enough.
She was after an understanding of nature, and there was very, very little that would stand in her way.
In 1902, after 4 years of arduous work, Marie finally succeeded in isolating 1/10 of a gram of radium chloride from 10 tons of pitchblende residue.
4 years to produce the kind of evidence that chemical science demands.
All of this effort so that she could actually convince the remaining chemists that this was a real, honest-to-goodness element.
She measured radium's atomic weight at 225.9, very close to the current value of 226. And she placed it correctly in the periodic table.
Radium officially existed. The incredulous chemists, and there were still a few, could now only bow before the facts, before the superhuman obstinacy of a woman.
Here she was, still basically a graduate student, and the whole world was beginning to talk about her discoveries. In just these 4 years, she's now discovered 2 brand new elements. Even more important, she's shown that this strange emanation, this radioactivity, is a feature of matter, not specific to one quirky little substance. And she's also developed a quite impressive technique for finding more.
This was the beginning of identifying elements by their radioactive power.
The same technique would soon be used by others to identify more new radioactive elements. In 1903, Marie Skłodowska-Curie became the first female scientist ever awarded a doctorate in France. By then, it was clear radioactivity was a pivotal scientific discovery, deserving of recognition.
There's no doubt that Marie Curie had done the lion's share of this work. And yet, when the time came to recognize this work, it very nearly went to other people.
A number of prominent French scientists nominated Pierre Curie and Henri Becquerel for the Nobel Prize in 1903. And in this letter, they didn't mention Marie Curie at all.
One of the nominators was Gabriel Lippmann.
It's quite remarkable, since Gabriel Lippmann was her teacher, her mentor. He actually presented her very first paper to the Academy. So he knew about her importance in this work and how central she was to these discoveries. And yet this cabal of Frenchmen just left her off the list. The idea that she could be an important scientist just didn't occur to them. She was totally invisible.
Pierre, and we have to give him total credit for this, turned around and said, I did not conceive of this idea. I helped with the work, but it was someone else's idea that made it possible, and that's Marie Curie.
Pierre was adamant that Marie needed to be included. He immediately wrote back and said, wouldn't it be better, from an artistic point of view, to award the prize to Marie Curie and to me?
In the end, Marie did share in the Nobel with Pierre and Henri Becquerel. She would go on to win a second, all her own. But the real prize was the magical substance for which she would always be known. Some nights the Curies would stop by the laboratory to admire the element Marie called my child.
They arrived in the rouleau monde. Pierre put the key in the lock. The door squeaked and admitted them to their world.
Eve Curie, in her biography of her mother,
Don't light the lamps.
describes the wonder of the Curies as they went into their lab one night and saw these glowing vials.
From all sides, we could see gleamings suspended in darkness, like faint fairy lights. Do you remember the day you said to me, I would like radium to be a beautiful color? Radium had something better than a beautiful color. It was spontaneously luminous.
The fact that radium glowed in the dark seemed magical, but it was also troubling because it almost seemed to violate some kind of fundamental physical law.
Scientists had known for some time that light is a form of energy. So if you distill something and it suddenly glows in the dark, you have to ask the question, where does that energy come from?
It's not changing shape, it's not interacting with the environment to get this energy, but it's just glowing infinitely. And we had no idea why it did that.
It was Marie who had the flash of insight. Perhaps some types of matter were changing from one kind to another, their atoms splitting apart and releasing energy in the process.
This theory of the source of the energy is very seductive. It explains radioactivity very well.
But it was an idea many chemists refused to accept.
Tell me, please, how much radium salt is there in the entire Earth? A few grams. On this shaky foundation, they want to overturn our understanding of the nature of matter.
Even the Curies were reluctant to accept it.
The Curies themselves, they wanted to think of elements as immutable, unchangeable parts of nature.
The idea that one could have transmutation from one element to another was very disturbing, even to her at first.
But the Curies' discoveries inspired others around the world to pursue this daring theory.
The idea that finally got pieced together was that the energy was in fact coming from the disintegration of these atoms themselves. Radioactivity was a sign that the atom itself was unstable. It could break apart.
This discovery implied something even more profound. Up to then, most scientists had believed atoms were the smallest units of matter, solid, unsplittable lumps. But if radioactivity was atoms falling apart, there must be even smaller pieces inside, still awaiting discovery. Thanks to this Polish expatriate, this graduate student, this young mother, scientists hoping to solve the mystery of matter now had a pressing new question to answer. What's inside the atom? Next time on The Mystery of Matter.
There's a fundamental quantity in the atom which increases by regular steps as we pass from one element to the next.
I think he must have been astonished.
Phil! The Germans have split the uranium atom.
Seaborg figured out how to turn it into a new element, plutonium.
No matter what you do with the rest of your life, nothing will be as important as your work on this project. It will change the world.
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following. To learn more about the search for the elements and watch bonus videos on the featured scientists, visit pbs.org/Mystery of Matter. The Mystery of Matter Search for the Elements is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS.
For me, Marie Curie is a story of perseverance. She just said, hey, you don't like what I'm doing? I'm just going to work harder and prove you wrong.
There's just so much about her and her stick-to-itiveness from the beginning. It's so moving and so wonderful.
C'est très bien.
Her courage throughout her life is an enormous inspiration to everyone, but especially to women.
She was certainly an inspiration to me. I come from a generation when it was also not quite yet fashionable to be a scientist. And here was a woman who had achieved it, to not only be a scientist, but to be a wife, a mother, a part of a community. Those are very hard to do all at once. She was able to do that. And as women came along, they could look at that and say, well, maybe I can do it too.
If you look a little different, if you're a different gender, a different race, there are many barriers to overcome. But you do what Marie did, which is you put your head down and you work harder.
Curie's legacy is manifold. She changed cherished truths or notions about how the world seems to work, what's the universe made out of. She challenged an equally steadfast notion of who should be contributing, who could play the game of science. She showed by example that there could be all kinds of people doing really breathtakingly important science. All kinds of people could have a hand in pursuing the mystery of matter.